performance data analytics, we start from the motivation why we are here. It's relatively straightforward because of the big data. We talk about data every day. We face a lot of data, text from your book and from the course material, images when you travel, take the photo and take the other images, and the video you recorded from the meeting. You will watch this video later. So that every day we will produce a lot of data, no matter what we are doing. So more pertinently, if you are a researcher for a machine learning research, you not only generate data, but also reuse this data to train the model. That iteratively, you can regenerate data and retrain the model. And therefore, we can say that we have a lot of data in our daily life. If we talk about data, let me know how large is your data. Byte, kilobyte, gigabyte, terabyte, or even large. Petabyte extra data you maybe you cannot access, but usually terabyte, gigabyte. You can type O at later part. Let me know which category you work with the data. And second question, are you experience performance bottlenecks when you handle this data? If you, I mean, if your data larger than gigabyte, how do you handle this data? Yes, let's come back. Yeah, we now because of the complexity and the size of data, we always use big data to describe this data set. This data quite large and quite complex. Complex is not only the text, images, and videos, or maybe a mixture of them. Okay, this means that somewhat it can be a daily challenge for us to handle this data. Handle means we capture this data, we store this data somewhere, we perform the data analysis, modeling, and visualization, and to get some information, useful information from this data. Yeah, how to capture this data, how to store this data, and perform data analysis, and we always come to these problems every day. Sometimes, well, yeah, in cases we use our brain to handle this data, what we see, what we do, and but in most cases we use tools to handle this data. For example, computer. So another issue arises: how can we use computer, or how can we effectively use computer to handle this data? This is the same of this workshop called high performance data analytics. High performance is the efficiency for us to handle this data, and we call it HPDA. HPD is subset of HPC, so HPC is high performance computing, which mainly focus on the data analytics. So the goal of this workshop is to precise, analyze, and visualize this data so that we can get useful information for the further usage to guide your performance or your activities in the future. The tool we are going to use is Python. I think there's no necessary for me to describe what is Python. This is the industry standard programming language, one of the most popular programming language for the data analytics, and now quite useful for this machine learning and deep learning applications. And the popularity of Python is mainly attributed to the rich ecosystem and the libraries. I listed some of here, ranging from the generic numerical libraries, for example, NumPy, Cython, X-ray, Numba, and Dask for this numerical computing, and also some domain-specific packages, for example, scikit-learn, TensorFlow, and PyTorch for the machine learning and the deep learning applications. Yes, that is why we're going to use Python. In this workshop, we will provide a broad overview of method to work with big data. using modern tools and libraries for storing and processing and analyzing this data. So specifically, this workshop will cover tools for efficient workshop with tabular data and multi-dimensional arrays and matrices, and the performance bottlenecks of the Python code, and also some method for the performance data processing via the parallel programming and the distributed computing. This is the main reason for us to deliver this workshop. And this is the let's move on to the next episode.
Can you see the web page with the lesson material?
Yeah, I can see it.
Okay, then I guess we can get started with this. So this first part will be kind of a large overview of what type of data we can work with, or we will find ourselves working with, how we can store it, and I guess give a nice overview of which formats are more suited for which application. And then we will conclude with some words about open science, how to share your data sets, how to make them accessible and citable, at least for those of you who are in academia, and what are pros and cons of having more open and fair science. I guess we can start from the very, very beginning, or the very, very smallest blocks. And the very, very smallest block when it comes to storing information is a bit. So this is the smallest amount of information that can be stored in a computer. And as we all know, I guess it's digital, so it can be either 0 or 1. And usually 8 bits are combined in a group to make 1 byte. And since each bit can either be 0 or 1, so only 2 values, a byte can hold at most 2 to the 8th, so 128, 256 distinct values. And so from this, we can move on to how these bytes can be used to store different types of information. So numerical data can be stored, of course, in binary formats, and the type of representation is very different between integer and floating point numbers. So when it comes to integers, integer numbers can be, of course, stored exactly. So the more bits or the more bytes we use, the larger numbers we can store. So if we assume that the first bit used for the sign, then 1 byte can represent from minus 128 to plus 127, while 2 bytes up to 32,767. So the more bytes we have, the larger numbers we can represent when it comes to integers. So far, so good. For floating point numbers, the story, of course, changes, because it's not just about the size, but it's also about the precision at which we can represent a number. So, of course, decimal number cannot represent it exactly as binary. So we will always have some kind of round-off representation error. And the more we manipulate these numbers, the more of these errors we will introduce. So especially in the beginning of scientific computing, a large effort went into designing algorithms such that they will not accumulate errors so much. And how to store this floating point, as they're called, numbers in a most accurate and at the same time space-efficient way. I would say today the gold standard is probably to use floating point numbers with a so-called double precision. So we use 8 bytes to store each floating point number. And this makes it so that, inaccuracy is under control, and we try to minimize the chances of numerical divergence when we're solving equations, for example. but very often in computational modeling, it is also okay to use single precision, at least in some parts of the code, so that we can reduce a bit storage requirements or memory requirements for large processing and still have a reasonable accuracy. For example, in many CFD applications with computational fluid dynamics, it is okay to use single precision unless we're dealing with, some types of problems that are very sensitive to divergence, like adjoint or things like that. Up until some time ago, single precision was also quite used in machine learning. Nowadays, there are more space-efficient ways to store data for data analytics applications specifically. For example, BF16, so-called, uses 16 bits, so only 2 bytes. It's not half precision. There's a kind of a trade-off, but nowadays it's very used, for example, to store weights of neural networks. So when it comes to machine learning application, actually, the number of bytes that is used for storing data is going in the opposite direction, and it is to comply with the fact that GPUs tend to have, of course, less memory than normal RAM. When it comes to text data, the first and arguably simplest character encoding is ASCII, American Standard Code for Information Exchange. And it was, for several decades, the most common type of encoding. With ASCII, we have 7 bits for representing each character. So we have only 128 characters that we can distinguish. In later decades, it became also common to use 1 whole byte to store characters. So we have an extended ASCII where each character is 1 byte. But still, that would only provide us with 256 characters. After 2008, a new standard came up that is called UTF-8. Well, it was in development for a long time, but after 2008, it became really more common. And the need for this came from the fact that, of course, we want to be able to store characters from other alphabets or ligatures and many other symbols that could not be fully covered by ASCII. So UTF-8 does not actually prescribe fixed size, but uses a minimum of 1 byte and up to 4 bytes per character. So when it's about data itself, in the end, it turns out to be either a number or some sort of text. Even, of course, images can be encoded to be numbers or text in most cases. But usually data comes with metadata associated to it. And for several applications, metadata tends to be as important as the data itself. And this can be any free form of information. For example, for numerical data, it can be units associated to it. For more, tabular data, like observational data, can be datetime or identification, for example, regarding biomedical data. And while most of the scientific data is either numerical or text, the associated metadata is very, very field dependent, and different, branches of science may have different metadata convention. So in most of the scientific use cases, for example, when it comes to simulations or experimental results, we try to store things such that metadata are bundled together with the data that they're referred to. And this, of course, has an impact on what kind of storage format we use. And I guess one of the main points that we're trying to make with this lesson is that there is not a one-size-fits-all solution. So different types of data require different formats. And I guess this is where we will take a nice deep dive. So when it comes to data and storage formats, or data formats mainly, we refer to 2 different concepts. So on one end is the data structure, so the model of the data itself as it is in our minds, in a way, and in memory. And this can be, for example, a table or some sort of multidimensional tensor or some grid organized type of data. And the file format, so how this data is actually dumped to disk. When it comes to the data format itself, we usually tend to have either tabular data, for example, data frames, for those of you who are familiar with already with Pandas or with R data frames. This type of data is structured into rows and columns. And very often when it is about, for example, observational data, each column has a name and a specific data type, while each row represents a distinct sample or observation. And each one of these observations or samples provides data according to each column. So let's say that, for example, we want to record the temperature in a certain place over time. Each row would be an observation, which will have, for example, the date and time and the exact value of the recording. And very often the simplest way to store tabular data and share it, at least when size is not a big problem and we don't have too many numerical columns, we will go through this in a few seconds, is to use the so-called CSV, so comma separated values. That is a very straightforward representation of how the data actually looks like. Another very common data type, mainly for numerical data, is gridded data structure, what we'll normally call a multidimensional array. And most physical sciences come with their own formats, depending, for example, if it's simulation data, the type of grid can be different across cases. There is a lot of convention in specific domains. But in general, what we tend to save is tables of numbers or grids of numbers, to be more precise. And how this can be stored for field agnostic formats are either HDF5, a hierarchical data format. This format is both a standard and the implementation of the standard. And it's a type of container for different types of arrays, and it bundles the metadata that comes with it. Another format is NetCDF, Network Common Data Form. This used to be implemented independently, but nowadays it actually uses HDF5 under the hood, but exposes a much more standardized and, from some points of view, simpler API. So they tend to be simpler to work with once you get it running, but you get very similar performance to HDF5. Ever since cloud became a thing, there is also ZAR that is optimized for the cloud in a sense that it supports parallel input and output. So each array tends to be divided into chunks that can be accessed independently. So for concurrent application is a very good candidate. And this leads us into what I would say is the core of this hour about scientific data formats. So we will try to give a nice overview of common data formats, what some of them are most suited for, performance considerations, and so on. So we have a nice overview here. Some of these formats are very Python related. The very first one is, for example, it's called Pickle, and is a Python native protocol for serializing data. What does this mean? This means that any or close to any Python object can be just dumped to disk, basically in the almost exact same way as it is present in memory, and can be recreated afterwards by an operation called unpickling. So having any Python object can be just dumped, imported in the pickle module, and later reread and recreated in exactly the same way. This is not used very often for scientific data. It can be useful for some type of concurrent applications, but I will not say it's a scientific data format. It's just very useful for storing small objects and then recreating them afterwards. It is not human readable, and I wouldn't say not particularly space efficient. But a good thing about it is that any type of, or almost any Python object can be serialized in this way. So when you have some type of object that does not fit any particular data structure, pickling can be a very effective alternative to just store it temporarily. The other Python native format is MPY. MPY comes from NumPy, which we will talk about in a few minutes. But it's basically a Python library used to operate with multidimensional arrays. It is still not human readable. It can store array data. So that what is inside these arrays can be very different data types, not necessarily numbers. It can also be arrays of strings, for example. But it has to be an array. And many NPY files can be bundled together in a zipped version of this that is called MPZ. So NumPy compressed, kind of. And that is basically a zip file containing several MPY. So these two kind of are restricted to pure Python usage or Python-based things, such as Paraview, for example. Whereas the others are more general. You can see that in some of these columns we have human readable. This connects to one property that different data formats have, that is how the data is actually stored onto disk. And this can be either saved as text files, so in ASCII format. So for example, a CSV file can be opened with a normal text editor, can be inspected visually. So it can make, in some cases, easier to visually check them if there are format errors. And they can be opened with any text editor. So looking at them is not the hard part. The cons with this type of files is that they can be slower during input and output. And they're not optimal for storage of floating point numbers. And that is because when we write floating point number as text, we are restricting ourselves to some level of precision. So we can only print so many significant digits. So either we need a lot of space to save many significant digits, or we have to sacrifice precision to reduce the size on disk. So when we're working with a lot of floating point numbers, and when it's very storage intensive applications, we tend to use binary formats, and those have very good performance in terms of input and output, and they tend to save space because the numbers are saved as they appear in memory and not in a string representation. Sorry. And embedding metadata is also easier because it doesn't ruin, so to say, the format of the file itself. And quite often they allow for chunked reading. So for example, if you have a very large data set, we don't need to load all of that in memory, but we can read only the parts that we're interested in. And most binary formats allow for this type of reading. So this can be very useful when we have very large data sets that do not fit into memory and we still want to read parts of it. The cons are that they require a specific library to be opened because they're very tailored to certain applications, which means that we need specific software or libraries of software to handle them. and sometimes even specific versions. And of course, they cannot be inspected visually since they're binary, so they're not supposed to be human readable. So going back to our table, apart from JSON, pretty much all of, and CSV, as I mentioned before, all the storage intensive formats are binary. So that is already an indication that when you're starting to have very large sets, you should move to some of those. JSON in particular is nice because it's human readable, but the same way very easily machine parsable. It came about in actually applications that have to do with the web. So it was the main format that was used to exchange data between, for example, different services in web applications. And the general idea is that it has a hierarchical type of structure with key value pairs. And it works well for long-term storage because it's kind of self-explanatory. But again, I wouldn't really use it for scientific data. HDF5 and NetCDF4, or NetCDF in general, we already talked about. The table is kind of clear on the fact they have very similar characteristics, and that's because nowadays NetCDF is based on HDF5. So under the hood, they do sort of the same thing. It's mainly the way we interact with them that can be more or less involved. Excel, well, is a proprietary data format, so I will not really spend too much time on this. What I would like to highlight is that if we're using tabular data, such as dataframes, libraries in Python specifically, such as Pandas, can open Excel files and also write onto Excel files. But I wouldn't say it's what it is done as a working format. After that, I will spend a couple of minutes talking about Feather and Parquet. These two formats came about with a boom of big data analytics. So they're very, very commonly used in machine learning applications. If you go, for example, on Hugging Face and look at models from there, the data and sometimes also the weights themselves can be saved in Parquet format, mainly the data actually. It can be quite useful for some applications where we need concurrent access. So Parquet has a very neat feature in which it allows for streaming processing. So the data does not actually have to reside on the place where it's been analyzed, but it can be streamed on the fly from a more high performance storage solution. So any applications such as data warehousing for long-term storage for later analysis and real-time analytics and streaming data processing, Parquet is a very good candidate. And libraries in Python such as Pandas can more or less seamlessly operate with it. Feather is in the same ballpark. It has to do with the Apache Arrow project, if you've heard about it. It's very space efficient. It does tabular data. In this case, we're calling it tidy. In the next hour, we will see what it means. It doesn't really do arrays, but it's a still quite used format. The good thing about Feather is that it was meant to be interoperable with other languages. So R and Julia, for example, have solutions to open Feather files natively. So if you work in a project where there are different technologies being used, it can be a good candidate. And I guess that with this, we went through all of them. So the general idea is that, yes, if you have some kind of machine learning, deep learning application, Feather or Parquet are very good candidates. Large data sets of numbers or also text, HDF5 or NetCDF4. JSON is more a data format, and CSV works well as long as you don't have a lot of floating point numbers and you still want to be able to inspect files visually. Feel free, of course, to interrupt if you have questions. Looking at the next few paragraphs of text, kind of summarize some of the things that I talked about. So CSV is again is a text format, can be opened with both NumPy and Pandas. We will talk about them in the next hour. But NumPy is a package to handle multidimensional arrays, whereas Pandas is a package that handles tabular data, so data frames. It's good for archival, but not really space efficient. In general, especially for tabular data, it's very easy to use because it's very easy to look at. But for array data, it works well as long as the array is only one-dimensional or two-dimensional, because we can look at it as a table, But if you have tensors at 3 or 4 dimensions, then it starts to, the reading advantage gets lost. But it's still quite popular, and it would be probably the first thought that anyone will have when trying to share data with someone else. HDF5 is binary. Pandas can handle those. There are also other Python packages such as H5Py that provides kind of very low level interface to it. And PyTables as well handles HF files, but when it's about tidy data. Then there are several other domain-specific file formats that rely on H5. Can be used PyVista as a package to handle mesh-based type of files. CGNS is very common in CFD. One interesting piece of trivia is that very often neural network weights are saved in a format that is based on H5, actually. So when we dump weights from PyTorch or TensorFlow, very often is a format that is based on H5 under the hood. Cool thing about it, or good thing about it, is that he embeds the metadata with it. So the format is kind of self-explanatory if the person who created it took time in describing it properly. And NetCDF is kind of the same thing. There are packages to handle both natively NetCDF4 files. And there is also an X-array package that we will talk about very soon that relies on NetCDF. And performance, I would say, is quite similar to HDF5, since under the hood it calls HDF5. But the API that it exposes is a bit simpler, and the structure is more standard. This format came about with a lot from climate simulations and Earth data, so there is a lot more standards about it. Whereas H5 is very, very generic. Then a couple of data formats that I mentioned, so Feather and Parquet for data analytics, and MPY just for quickly serializing and loading NumPy arrays from disk. One thing that I would like to talk about is X-arrays, because so far we've talked a lot about, data arrays. So when we have grids or tensors, multidimensional numbers somehow, and data frames or tabular data when we have rows and columns. The X-array package is something that builds on top of both NumPy and Pandas and tries to bridge between the two worlds. So it offers us arrays multidimensional arrays where the dimensions are labeled. So we have our matrices of data, but both rows and columns can actually be named. And this can lead to really nice code to write in some ways, because rather than having to remember the structure of how we saved, for example, a certain array, how we decided to orient it in memory, we can work with named dimensions. And there is an example further down that actually we can look at now, and then go back to the fair data later. So this exercise is derived from the X-ray tutorials. There's a clickable link. It's very nice documentation. And I will just show you a bit how the code looks like, but I invite you to try yourself for a few minutes and collect any impressions. So an X-ray dataset is a collection of different data arrays, they're called. In this case, we have one called A and one called B. And that share the same coordinates, so the same labels in a way. So in this case, we have a dataset A that is just a matrix, of random numbers. But what is interesting about it is that the columns are named X and or we're defining data that it sits on X and Y, which means that I can call this array with instead of using integer indices, I can call it with the name of the dimension that I'm giving beforehand. They can be very easily dumped to disk using the 2net CDF. So X-ray uses heavily netcdf actually. And then you can open it back and recreate it in more or less the same way. You can open a Jupyter notebook, or you can also do it directly from the Python interpreter, So I can just show you how it is here. So you can just import, X-ray as XR. And then you can simply copy paste this code or type it yourself if you're feeling like it. Oh, I didn't import NumPy. And then I can do this. And then you can try to inspect them by just typing, for example, DS1 and try to look at the dimension. And you can take a few minutes to do it yourselves, let's say until 10 or 10:05. And then we can devote the last few minutes to talk about open science and fair science principles. And after that, we can take a short break and move on to something more practical. So how to interact with normal arrays and data frames. So I guess we can take a couple of minutes, like until 10:05.
Yeah, we can take 1 minute. I hope that you have installed the program environment in your computer. Either you can either use Lumi or your personal computer for the accesses. If you come to any problems about the installation or the package issues, please let me know, and we can use breakout rooms, and me and my colleagues will try to solve these problems as soon as possible.
It's coming up. I just wanted to take a few minutes. You can still see my screen, right? Yes. About sharing data and fair science principles. And after that, we can lead into the break. So there is an open science movement that encourages researchers to share research output, not just in the form of articles, traditional academic publishing, and of course supplementary information, but also sharing the data sets themselves. And this has become all the more important since machine learning became a thing, both in the sense of text generation, but very often also for scientific machine learning. So, of course, open access publication of both reports and the data allows for better peer review within limits a list. And since science is mostly funded publicly, also results should be publicly available. And, the more data is available, the more access people to have to tools that can help to solve really important questions, On the other hand, too much unsorted information can be overwhelming. It is already overwhelming, and there is a lot of research into how to use tools to navigate the large amount of data that we're exposed to daily, and can be potentially misused. Of course, science is already very big now, and increasing the scale can make it, reproducibility and verification of discovery a lot more difficult. But when we do choose to make our datasets available, one nice way of doing it, I would say, is to use so-called FAIR principles. So it's a data management philosophy, I would call it. It tends to come about, for example, if you're applying for grants, how your research data can be fair. In this case, FAIR is an acronym that stands for findable, accessible, interoperable, and reusable. So findable means that we would ideally like to make our data available in some standard repository. And this nowadays can be done quite easily because we can get GUIs, DOIs, also for data on places such as Zenodo. And there is an example about that just a couple rows after this. And accessible means that once it's in this up on this repository, people can actually access it. This, of course, needs to be done in a responsible way. So when it comes, for example, to medical data, there needs to be more procedures and ways to making sure that data is safe. One important point that is often overlooked is that accessible is not the same as interoperable. So if I make my data accessible in some, very exotic format, maybe proprietary to some piece of software that is not really usable by most people because they will need to get the same software or, make a lot of effort. So it should be made available as much as possible, of course, in some format that is open and freely implemented by anyone who would like to look at it. So, if I have to save a table, I will do it in CSV rather than PDF to make it easier. If I'm using, data coming from some flow simulation, I wouldn't use the native format of the software if I'm using a proprietary software, but rather some more interchangeable format. In this case, we talk about CSV. Oftentimes we can do a lot better, but that's the general idea. And reusable, of course. So once it's there and I can look at it, I can actually use it I'm under a license that allows me to use it to further science even more. So this is referred to as open data. And in some cases, we don't really get around without using, or we cannot get around the fact that we have to use non-open software. But FAIR, in this case, stands for doing it as much as we can. And there are several data repositories that can be used to make our data available. I would say most likely the most famous one is Zenodo, that is general purpose, and it integrates quite well with GitHub. So this is nice in that sense. And you can share files up to 50 gigabytes. So for many cases, it can be a good solution. Figshare was originally born to share, as the name says, figures, images, videos, but we can also have whole data sets there. And both of them allow us to mint DOI, so that can be shareable and citable. And a couple of others that are born, for example, in Europe, such as UDAT and Open Science Framework is also quite interesting. A few of them are mainly aimed at Swedish, both researchers and audiences. So Berlin Center for Climate and Geodata is one of them. Data Guru. There are a few where we can have omics data. And there is a small example here on how we can use Zenodo to mint DOI. And this works quite well because we can just connect a GitHub repository to it. And after that, it has a DOI and it's verifiable and citable. And you can actually test this yourselves right now using a sandbox. So this is a test version of the real Zenodo platform. But if you want to try and experiment and see how this works, you can use this sandboxed version. And yeah, it's very good for also preserving the history, for example, of data and code that you're producing. And nowadays, I would say something quite important to have exactly reproducible science. So just to conclude on what we talked about in this first hour, well, file formats matter is a very big message in this. So I would say that the really, really important thing that if you forget anything else, at least remember that is for large data sets, use H5 netcdf or something binary, especially if it involves many numbers. CSV and JSON can be good if you need to look at a file manually. And for tabular data, CSV is actually a relatively reasonable choice. Xarray can be a very, very nice tool if you want to have more readable and also understandable way of working with arrays, because you can name the dimensions. So, for example, if you have a three-dimensional array where you have data on a 2D grid for several time steps, then you can actually call your columns X, Y, and time, which means that you don't need to embed a lot of the separately metadata with it, but you can discover a lot about the content just by looking at it. And of course, in them, you can embed metadata anyway. And it can be good to share results of your research, not just in the form of articles. And more importantly, from my point of view, also having a recorded history of your data and your software means that science can be reproducible, at least having access to the initial raw data if it comes from experiments. And in today's, reproducibility crisis, I think it's one of the first and very important steps that we can do to have science as reproducible as possible. Yeah, here it comes. Okay, so objective for today, or for this part of this of today, are why Python is sometimes considered a slow language. This is kind of true-ish, but we will see some ways to solve this. And then the two probably kings of Python data processing that are NumPy for arrays, gridded data, and Pandas for tabular data frames. So is a thing that probably you might have heard. Python is slow. This can be true sometimes about system or base Python, but it doesn't mean that there is not anything that we can do to solve this. And NumPy and Pandas are probably the two most important steps that have been done to alleviate this. But first, maybe we should give a look at why this happens. And this boils down to how Python was designed as a language. So nowadays, computer programs are almost always written in a high-level, human-readable programming language, and then translated to instructions that a machine can actually execute, so that the processor understands. And this can historically happen in two ways. We have compiled programming languages where the translation is done before execution in a separate step by a compiler. So we write our code, for example, C falls into this category. We write code, we use a program called compiler that translates it to machine instructions, and then we execute it. And this means that the compiler can do all sorts of clever things to make our code go faster, including the fact that very often for a lot of the data that is inside the program, it can allocate beforehand the memory that it needs, which tends to be an expensive operation. So the fact that it can be done beforehand is a huge time saver. The second category is the one interpreted languages, where this translation is done on the fly. So when we run a Python script, Python is an interpreted language. There is a piece of software called interpreter that, while we're executing the program, will take care of translating it into machine instructions. And this is very useful for to have a very dynamic behavior of our programs, in the sense that it's very easy to do rapid development, because we can test our program as soon as we write it. We don't need a separate compilation step, and this makes for very short development cycles. This, although, comes at a cost of usually decreased performance, because the compiler cannot really do, there is no compiler, so there is no optimization that can be done beforehand. There is also a set of languages that work with just-in-time compilation, where the compilation is done just before it gets executed. So you try to get kind of the best of both worlds. Languages like Java, where there is an intermediate compilation step, but it's still not to machine language, but to some in between that is a bit faster. But in general, yes, compiled versus interpreted is the dichotomy in this case. And so this is one thing, Python is interpreted. Another issue regarding performance, but not productivity, is that Python is a dynamic language, which means that variables are assigned a type, so string, integer, complex data types, only when the program is run. So there is nothing that the interpreter can do beforehand to optimize the flow of the program, because it doesn't know what type each variable has. Whereas a compiler can, analyze the code extensively and optimize it before execution. This is very nice from a programmer productivity point of view, because Python leaves me very free to use my variables as I want and put whatever I want inside them. But at the same time, it comes with a performance penalty. And the other thing is the data structures in Python. So there are some built-in data structures, such as lists. So, concatenated, ordered sequence of data, and dictionaries that instead are key values type of data. Are very flexible and very generic. A list in Python is more like a bucket than a list. I can have a list that in position 1 as a number, position 2 as an array inside, position 3 as a struct. It can be anything inside, which means that there is a lot of overhead from the interpreter inside to make sure that all this stuff can be implemented as generically as possible. This also means that the interpreter cannot allocate memory beforehand. So every time I extend a list, I have to make room for it or link it to somewhere else in memory. So this is very nice for the programmer because it's very expressive. But it's also probably the main cause for performance bottlenecks is the fact that we cannot optimize anything beforehand. And especially when it comes to lists, this is kind of summarized in this picture. So Python list is a collection of many different types of objects, including other nested lists. And since the interpreter cannot know beforehand how big they're going to be or what else is going to be added, it cannot, put them together in memory, and this can lead to problems. When we are doing scientific computing, very often we will handle numerical arrays. And this library called NumPy is probably the most fundamental building block of scientific computing in Python. It's written in C, but exposes this Python interface. So to the user, it doesn't really matter. It's like writing Python. But it gives much better performance. And, it offers a huge ecosystem of mathematical functions, random numbers, linear algebra, FFTs, all sort of things that you may think of. We will look at them in a few minutes. And probably the most important optimization that NumPy does is to have homogeneous data structures. So when I create my array, whether it's one-dimensional or multi-dimensional, all the fields of the array have to have the same type. So I can have an array of integers, an array of floating points, an array of strings. I'm not limited to numbers, as long as they're all the same. Moreover, NumPy vectorizes mathematical operations, which means that if I want, for example, add a number to an array, I can do it on all the fields of the array at once. And this can lead to much faster precompile code instead of using for loops. So most of the times when you're working with numbers or with arrays, actually, you will use NumPy. And the core of NumPy is the ng-array type, which stands for n-dimensional array. And compared to a Python list, you cannot hold anything that you want inside, or you can hold anything that you want inside as long as they're all the same. So you can't have different types inside the same array. Ng-arrays can have multiple dimensions. So 1D array is commonly called a vector, 2D array is a matrix, 3D, 4D, they don't have special names, but you get the gist. And when we vectorize our operations, so when we don't write for loops, but rather act on all the array at once, the operations are very fast. There are some things that remain slower, and those are, for example, appending elements. So a common thing that we will talk about, and also you will hear throughout your journey, is that it's usually a good idea to pre-allocate arrays. So if I know that I'm going to be working with a certain matrix, for example, of which I know the size beforehand, then it's good to declare it beforehand and then fill it up. And this is because if we look, for example, here at what a NumPy array looks like, it's all stored together in memory. So I can say that I need, space for 1 million numbers. Then the interpreter will set aside space for exactly 1 million numbers in memory. But if I want to add another one, it might not be able to do it contiguously to the rest of the array. So we'll have to, copy it around and reserve other space, and all this gets very, very expensive in terms of execution cost. So pre-allocating is key, and as much as possible, trying not to append or pop elements from a NumPy array. The data types that we can have inside an array can be many, and actually more than native Python has. So we have 5 numerical types, or 5 basic types for the kind of numbers, and in this case also booleans. So booleans are true or false, integers, unsigned integers, floating point, and complex. And for example, we can actually look at it. We can import NumPy as MP, and yeah, we can just create a floating point variable. Float 32 means that it's a single precision because it only occupies 4 bytes. And then we hold this number. And we can have, for example, create here an array with 3 elements that are unsigned integers. This A range is quite similar to the native Python range. I guess you're familiar with that. And with the D type flag, we specify which type of data we want to have. So 0, 1, and 2 are unsigned integers that occupy 1 byte. And we can also use some native functions from NumPy to convert. So for this, we can convert it to float, and now our 0, 1, 2 are floating point numbers. Yeah, you can see here that are floating point numbers. What happened here was that this Z as type does not modify in place, but it returns another array. That's why when I print against that afterwards, I still get my unsigned integer. So this returns something else that if I want to save, I have to assign. So I can be, for example, doing something like this. And then A will store my newly built floating point array. So how do we create NumPy arrays? One way is to do what we've just done. For example, using functions like arange and linspace. Arange is kind of like the Python range. So we'll create a list given we can pass it. Let's do it again. p.arange 10. So if we give it only one argument, it will assume that we're going from 0 to the end with spacing 1. But it's a lot more flexible than the native Python version. So we can have, for example, give it the start, the end, and the spacing that we want in between. So in this case, arange will compute how many numbers with spacing 0.02 can fit between 0.1 and 0.2, and give me an array of a corresponding size. So arange is useful when we know the start and the end of the spacing. In some case, we want to do the and it will give us the correct number of items inside. In some cases, we want to do the opposite. We want to subdivide a certain range into a certain number of items, which we don't know beforehand. So we want Python to compute the spacing for us. And this is what the linspace function does. So for in this case, for example, we're going from minus 4.5 to 4.5. And we want 5 numbers. Using the linspace function, it will compute the spacing for us and given the how many items we want. So they kind of do the similar thing, but starting from different premises. In one case, we know the spacing. In one case, we want the number of items, but they generate sequences. I told you before that pre-allocating is key when we talk about NumPy arrays. One way to create is to convert a Python list to an array. If we do that, we have to make sure that the list contains homogeneous data types. NumPy will not particularly complain if we have a list full of miscellaneous objects, but it will have terrible performance. So if you have a Python list, for example, you can say that B is equal to a list 1, 2, 3, 4. That we can say that B NumPy, for example, is equal to NumPy array of B. And we can prescribe the data type, but in this case, NumPy will be clever enough to understand that these are all integers. But in case, I can also force it to cast all the numbers inside to float. And then they will all be converted to floating point numbers. We can also force it to be complex numbers, for example, and then we'll append an imaginary, you can see this example here, it will append 0 as the imaginary part. I can do this. Yeah. J is the Python indicator for the imaginary unit, not I, but apart from that, it's pretty much the same. These were all one-dimensional vectors. We can also have matrices. So for example, we can have a list of lists. So 1, 2, 3, 4, and then 5, 6, 7, 8. And then this can become, again, we can convert it to an array. And in this case, of course, again, the conversion to complex, but you can see that now we have 2 rows, and we can check the shape using the shape attribute. So in this case, I have 2 rows for columns. And the size attribute will give me how many items are contained. If you're not creating arrays based on a list, but rather we're going to fill them up, for example, reading from a file, the pre-allocation can be done by using instructions such as NumPy zeros or NumPy empty. And there are some examples here. So for example, if I know that in a file I have, I want to represent a matrix 4 by 6, then I can pre-allocate a matrix, giving the dimensions as a tuple, and then passing it the value type that I want to have inside. So this, in this case, will be full of 0. There is a very similar one that is called once, that just fills it up with 1. Full can be used to prescribe any value that we want. And then we can also use empty. Empty will just allocate the memory, but not really changing what's inside. So it will just take, I can show you an example. Empty will just tell the interpreter, look, I'm going to need a 2 by 2 matrix at this location. And the compiler will just reserve that memory. In this case, the memory happened to be full of zeros, but it could be anything. So in this way, I can, reserve the memory, so the interpreter knows that that's the size of my array, and most likely it's not going to change. And then fill it up, for example, reading from a data set, a file, any other type of processing that I want to do. Lastly, we can also create arrays based on the shape of other arrays. So for example, here I have an empty array 2 by 2. I can create another one with the same shape. And this can be, for example, mp.empty like d. and then it will create another array of empties that, or another array 2 by 2 without actually changing the memory inside. So in this case, it still happens to be full of zeros, but I can do also something like ones like D, and it will do the same thing by filling up with ones. So if you've written some MATLAB, this might ring several bells, probably, but it's all fast ways to create arrays. And again, the important thing is to pre-allocate them as much as we can. So normal arithmetic operations are applied element-wise in NumPy. So if I have, for example, an array 1, 2, 3, and an array that is 4, 5, 6. If I sum them, it will add the numbers one by one. So we'll do 1 plus 4, 2 plus 5, and 3 plus 9. Same thing if I do a division. So normal arithmetics is done element-wise. The same, of course, also goes for 2D arrays or any dimension for the size. As long as the dimensions are the same, they're done the sum or all the common arithmetic operations are done element-wise. Indexing of arrays is quite similar to Python. So let's say that we have, let's make maybe a larger array of 10. So I'm now going from 0 to 10. I can slice one single element, indexing as in native Python starts from 0. I can do some kind of slicing where I get more than one element. So the colon operator is used to prescribe beginning and end. As again, in native Python, the first element, the start, is included, whereas the last is excluded. So in this case, 0 to 2 means that we're grabbing 0 and 1. We can do it from the end. So if we apply a minus before the index that we want, that will start from the opposite direction. So we're saying grab all the numbers from the implied 0 in the beginning until the second last excluded. We can also prescribe a spacing. So for example, from the beginning to the end, every second element. Oops. And this will take any element. So the whole syntax will be for subslicing is start and -1, so to say, and step. So this type of slicing will give us from where we want to start to where we say -1 with a spacing that we want. NumPy also supports some more advanced indexing. So for example, we can prescribe a list of the indices that we want to extract. And from parentheses. Nope. No, sorry. Yeah, it was okay before. Never mind. And another interesting feature is that we can do a Boolean indexing. So we can prescribe, for example, a condition getting A where A is more than 5, for example, will give us the parts of the array that satisfy this condition. There is also another function that behaves quite similar, that is NumPy where we can put actually any Boolean condition. One thing to keep in mind is that integer indexing will return a view on the array, which means that we can modify things in place. So if I say, for example, A3 is equal to 100, then this will modify the original array. But if I do it with a fancy indexing, as we was dubbed in this case, this will create a copy of the array. So that's something to keep in mind. This can also be extended to any dimension of arrays. So in this case, we will have, of course, I'll just maybe copy this, it's quicker. We have to provide as many indices as dimensions that we have. So the order is row column. So this will extract the second row since the rows start from 0. We can be explicit also and say that we want the second row and the whole column. This will give the same thing. We can extract a whole column. So in this case, we want the whole row, but the 0 column only. And of course, mix and match the two. So if we want to get the lower right corner, for example, we can do the same. And same thing with Boolean indexing, of course. So yes, to keep in mind just that all these types of slicings allow us to modify the memory in place, whereas fancier types of indexing, they return a copy. We can aggregate values using some kind of reduction operation. So for example, we have our data array. We can return the sum. Oh, sorry, the maximum number, for example. That would be 12. We can return the sum. We can return the minimum. Common reductions operation are supported. What is also interesting to do is that we can do it only along certain axes. So we can aggregate, basically reduct only over some dimensions. So given our data array that we created before, we can take, for example, the minimum along axis equals 0. So, so what this is doing is basically going in each row and getting the minimum. Sorry, or let me rephrase to be more clear. So it will apply the minimum operation across all the rows per column. So it will select all the rows in column 1 and or column 0 actually, and get the minimum, all the rows in column 1, and so on. If we give it axis equal 1, it will go the other way. So it will take all the columns in row 0, in row 1, and in row 2. So I guess a good way to be on top of this is that the axis says which parts of the array will enter the whatever computation we want to do. If we give axis equals 0, it will select the whole row. If we give axis 1, it will select all the columns and do the operation in the corresponding axis. Another common thing that you might find yourselves doing is reshaping. So in this case, data is a row vector, and we can reshape it to become a 4x3 matrix, for example. And the other way, for example, 3, 4. it will shuffle things around. NumPy arrays, unless we say explicitly otherwise, they're stored in so-called row major format, or C-like format. Maybe we'll come across this term. This means that if we create, for example, a matrix like this, this will be saved in memory going row by row. So if we look at the memory, it will be 1, 2, 3, 4, 5, 6. In other languages, it might be 1, 4, 7, 10, 2, 5, 8, 11. This can have implications in the reshaping. So if we don't say anything, it means that it will take our row vector and make a matrix, put in the numbers from left to right, from top to bottom, rather than from top to bottom and then left to right. You can enforce also the other ordering. There is a flag that you can pass to it, but just, it's the rows. It will go row by row. How the arrays are passed around when we reference them, for example, or when we slice them, in general, is references and views, which means that, for example, we have our a vector can be, we have this vector. If we say that b equals a, in this case, we're saying that b is like a pointer to a. So if we do a modification to b, it will also be reflected in a. So for example, b, if we change the first element of b to be 100, so b has 100, but also a. So b is just a label that we use to refer to a. It's not a copy, it's a reference. If we want to have b to be exactly a copy of a but independent, so literally copying the memory, then we can use the copy method. And then if we restore, for example, in b 0 equal to 0, then we will have that b return to the original state, whereas a still has the 100. Same thing applies to slicing or indexing, as long as it's not the one where we pass a list of indices, what we call the fancy indexing. So if I do a slice, this just references the array. So if I make a change, it will be reflected to A. If I want C to be an actual copy of the first 3 elements of A, then again, I have to use the copy method. And in this case, a modification in C will not affect A. So in general, yes, assignment and slicing gives us a reference to the memory that we're operating with without actually copying it. And yeah, something to keep in mind. Input and output, we can write NumPy arrays and read them from files. If we want basically CSV files, ASCII files, we can use the save.txt and load.txt methods or functions, and those will basically write CSV files. There is a whole number of options that we can pass to it. For example, giving titles to the columns, specify how many significant digits for the numbers. You can find all of that in documentation. But generally speaking, an NumPy array can be saved with a save.txt and loaded back with load.txt. We can, of course, also dump into a binary format if we have large arrays with a lot of numbers, and that can be done with the save.z. So we can tell, for example, to save in a file called hi.npz, and we tell it that we want to have we want to save our C array and the name that we want it to have in the file. So with this, we will have a hi.mpc file saved, and then we can load it again. Yes. So this, let me do it like this. So let's say data is equal to this. And then data behaves like a dictionary where the key is given by this. So what we gave in when we saved it. So I can call data C in this way, and it will have been the array that I saved. Yes, so we can save both ASCII and binary. That's the bottom line. We can generate random numbers choosing the distribution. So we can import a NumPy, or actually we don't need to in this case, but I can do numpy.random.random. And we can pass the tuple with a shape, and we generate two random numbers. With a uniform distribution, we can prescribe normal or sample, for example, from a given array. We can do polynomials to do polyfitting. This maybe can, I'm not going to spend time on this, but it can be useful. What interesting, it can be linear algebra. So we have very efficient primitives to calculate various types of matrix products and vector products. We can diagonalize matrices, so computing eigenvalues and eigenvectors, solve linear systems. So for example, let's maybe make it a bit quicker. So we can create this 2x2 matrix and this one. Oops. And then take the dot product. So we can say that C is the dot product of A and B. Did I copy something wrong? Oh, yeah. And then C will contain the dot product. Many of these, they also have shortcuts. Like we can call the method directly, mp.dot, or also use that dot directly. We can also solve a linear system given the known values. So we have 1 and 2. Then we can do solve. And this will solve the linear system corresponding to Cx equal B. Under the hood, NumPy uses some kind of BLAS implementation, which is basically saying that we have high-performance libraries specifically tuned for linear algebra tasks that are written in C, and they're just called seamlessly from NumPy. So it doesn't really matter to the user, but it is to say that there are very high-performance functions used to perform these computations. And then the NumPy ecosystem, this comes a bit later, but I can just mention it now, that NumPy ecosystem is usually extended with something called SciPy, that is a library built on top of it, and offers a huge number of functions to do day-to-day scientific computation tasks. So, for example, numerical integration, fast Fourier transforms, a lot of tooling for signal processing, such as, again, FFT or Welch or wavelet transforms, or linear algebra, even compared to basic NumPy, sparse matrices, a lot of statistic toolboxing, statistics toolboxing, and various type of interpolation. So some of those were implemented in Python. Many others actually interface to, battle tested C or Fortran libraries, and they are very well documented. So chances are that if you're trying to do, normal data analysis tasks, there will be something written in SciPy that will save you a lot of trouble. And there are a couple exercises that you can look at yourselves at the end of this hour. I would like to take the remaining half an hour to look at the other very important library that is using Python, and in this case is to use to deal with tabular data, so rows and columns of data. Probably the most widely used one nowadays is Pandas. There is also a kind of new player on the field that is called Polars that has very high performance, but is long. But probably most of what you will find is Pandas. And by its high performance and to use data structures and data analysis tool for tabular data, it actually builds on NumPy, but it works very well for tabular and also time series data. NumPy could deal with structured arrays, so arrays with mixed data types, as you would have here, but it will do it with very performance. Instead, the starting point of Pandas is that each column in your table can have a different type, and you still get quite good performance. So the core data structures probably are a Pandas series that is a one-dimensional NumPy array that has an index that we can use to access the data, and a data frame. A data frame is pretty much the same data frame as R, if you're familiar with it, but it's a table of values that is labeled on the columns for sure, and sometimes also on the rows. So each column label and row as an index, but it's not necessarily labeled. Data frame can combine multiple data types. So each, as long as each column is homogeneous. So if you have worked with tabular data sets before in your life, you may come across the concept of untidy or tidy data formats. It's a concept that came about apparently officially around 10 years back that described the ideas behind it. Untidy and tidy are two different ways of representing the same data in a more or less structured way. So let's start by importing Pandas as PD, and we can have a look at this. So first of all, let's say that we import this table as it is. So we have runners, and this is very easy to read for humans. It's not exactly explicit, but you can most likely understand what each column is. So these are different distances of arrays, 400, 800, 1200, and 1500. And you have, for each row, a different runner pretty much with the time that he made on each one of these distances. And this is also because this table is very small, it's very easy to understand, but it's not optimal because you have several variations, or basically a lot of data per row, because what runner one has done in each one of these distances for a single row. Tidying this data in Pandas is done with an operation called melting. I will just apply it now to give you an idea of what this means, and then we can discuss it. In this case, instead, we're explicitating, making explicit what the columns are. So we have a column for distance and a column for time. And each row corresponds to a single observation. So observation 0 is runner 1 at a certain distance with who made a certain time. And then observation number 2, well, we index 1 is runner 2 on the same distance who made a different time, and so on. So we're not basically globbing data together. So tidying data from a strictly statistics point of view means that each column is a variable, and each variable has a column, and each row is an observation, and each observation is a row. So this is very often is called a long data format because of the reason that you're seeing, how much also because how much longer it is compared to the way that we wrote it the first time. And it allows, there are some advantages regarding strictly performance. But what I think matters the most is that this is much easier to, filter, group, aggregate, join, lots of daily tasks that we do when we're dealing with data analysis. So, for example, making statistics of different runners over the same distance or different distances for the same runner works exactly the same way. Whereas in the first example, having the statistic of one runner was easy, but doing the other way might have been a bit more involved. So the workflows that we follow are more standard, I would say, when you work with tidy data. And you can read the original paper where this concept came along. I find it very illuminating, might help you too. And let's just go through some examples. So the general pipeline is that we read datasets that we already have or we download from somewhere. We can do some initial exploration of the data. Then there's a bulk of the flow, or what usually takes the 80% of the time in this analysis is actually the pre-processing and the cleaning. And here we can have renaming, reshaping, changing types, lots of, not directly analysis related, but that are necessary in order to perform the analysis. Auto-handle, for example, missing data, we will see in a second. So we can start with one very famous data set that is the one of the passengers of the Titanic. It's used very often. And it is stored on the Pandas GitHub repository. And Pandas lets us import a data set directly given a URL. So we can just take it from there, and it's saved in CSV format. And then we tell it that each passenger has a name, and we use the name as the index for the row. So that rather than, make it give us an ID given by Pandas, we're telling it that we want to use the name as an index. Missed an underscore. Yeah. So we have our Titanic dataset. Maybe I can make something like this. NumPy can understand a lot of other formats. So we can read Excel, we can read H5, we can read JSON, and correspondingly also save to any of these formats. We're getting already some information. So we have 11 columns, like 11 observables, or 11 variables, sorry, and 891 observations. Pandas comes with some tooling to, to give a quick look at the dataset. So we can look at the head, for example. This is the first 5 lines of the data frame. This one, I don't have a little space, but I can, for example, print the columns. So just to see what is saved here. So we have 11 columns, including a passenger ID that came with a dataset. Whether he survived or not is an integer that in this case will be 0 or 1. The class, sex, age, cabin, whether actually embarked or not. We can directly get statistics by using Titanic.describe. And this basically for each column will give us some basic statistics like simple count, the mean, standard deviation, minimum, and 25, 50%, and 75 quartiles, and the maximum. So this can help us to have a quick look at the data set. And for example, yeah, we can see that the 38% of the passengers survived. Now here I don't have a lot of space for the other columns, but we will see, for example, the average age and how many survived and so on. How do we index a data frame? We can go, well, of course, by row or by column. To inspect one column, we can use either a dictionary-like interface. So each column is a key of the dictionary. In this case, we know we have a column called age. So this will print the index that we chose to be the name and age only. Another way is to use also a dot syntax. This will give us exactly the same thing. So each column is either a key of a dictionary or directly an attribute, as if it was a structure. To get the names of all the columns, we can use the columns attribute. And the ttype in this case is object. However, the rows also have names. And this is what we did in the beginning when we imported the dataset by saying that the index column in this case was the name. We're not forced to do this, but in this case we gave the index as the name as the index. So if we print this, it will tell us that all the indices are the names. We can, before we looked at a single column, but we can select and also set the values of single or multiple rows, columns, and elements. There are many, many ways that we can index stuff. So for example, if we want to select a single row or a single value by the row, we can use the lock function. And this, for example, with the name gets a bit impractical maybe, but this is basically us selecting the row and then the corresponding column. So if you can see, this is not too different from indexing a NumPy array, except that the first and second dimensions are names of columns. And in this case, we will go through it in a second, but it told us that the value is not a number. This is what Pandas does when there is a missing value in the dataset. So we don't need to have values for all the cells in the table. If you're missing one value, it will be replaced by this none that stands for another number. And we can slice, for example, all the columns from survived to age. So it survived, and it was in third class, and it was a male. So this would have taken all the columns in order between the columns survived and age. We can do the same thing also directly with numbers. So if we know, for example, which row number a certain value as, we can just use the iloc method as in integer location. So here, for example, 692, and then columns for 3 to 6. And this went to the same person that we just knew was number 692. We can also replace a whole column with some values. Another interesting that we can do is to do Boolean indexing. So for example, we can extract a subset of where the age is more than 70. Oops. So this lets us filter all the passengers that were older than 70. So what am I doing here exactly? If I do Titanic age more than 70, this will, I can actually copy paste it. It will return a so-called Boolean mask. So it will basically apply or check this condition for each value in the age column, and it will return a false or true. So I will have basically an additional column, and so to say, that holds whether this condition is true or not. And then I use this to index through the Titanic dataset. So I'm basically telling check in the age column of Titanic where it was less than 70, and use all these indices to extract data from the Titanic data frame. And I can do lots of similar things as long as I provide a Boolean value. So in the example done here, for example, I'm looking at the name, so Titanic index. I'm turning into a string, and then I'm checking whether it contains the name Margaret, and use that Boolean mask to index through the Titanic. So it's a way to extract all the passengers that have Margaret in their name. As I briefly mentioned earlier, if the data set has missing data, we will have the value not a number. And by default, it is excluded from the computations. We can find missing values and do what is relevant. So for example, we can choose to drop either all the column or the whole row where there is a none, or both. Replace them with any value. We can fill them with something else. So this Titanic dot is not the number. We return a Boolean mask, much like the one that I created before with the age more than 70. So we create a table where in each location, it will tell me true or false, depending if that particular cell is true or not. I can drop all the missing values. So in this case, he has removed all the rows where there was at least one missing value. And I can choose how to do it. So if I want to remove rows where all the columns are missing value, so I pass it how equals all. Or if I want to just drop where any of the cells is not a number. I can also drop it, for example, from just one column. I can replace them. I can do a lot of manipulation. Just for the sake of time, I will move to the next part, that is group by. And this is part of probably the most common workflow that is done with tabular data analysis, which is split, compute, aggregate. It is what dplyr does in R, for example, if you've used R in the past. So group by allows us to split a data frame and aggregate the data in groups. So for example, we can create a new column in the dataset called child to indicate whether a passenger was a child or not. So to create a new column, I can just address it as a key. So this is us basically adding a key to a dictionary. And I do that by taking the age and checking where it's less than 12. So our threshold for a child is 12, and this will add a child column to Titanic with a Boolean flag that says true or false. So I will get something like this. And then I can do group by. Group by basically splits or gets us together columns based on the variables that we pass to it. So group by, for example, we can decide to stratify our data by sex and whether the children or not, as we just created. So what this is going to do is basically stratify the data, so gather it by sex, and then within sex, whether they were children or not. And then what I can do is take sub-slices, kind of. So take the survived column of this stratified data, and then compute the mean of it. So this will basically create a smaller data frame where I'm aggregating statistics based on some criterion that I choose. So in this case, I will have the sex that can be either male or female, and then within the sex, they can be children or not children. And the last thing that I'm showing is the mean of the survived column over these 4 different groups. And the last operation that I'm doing, which is this mean, is a reduction operation, it's called. And I can have several functions I can pass to it. For example, standard deviation, the maximum or the minimum, cumulative sum, median, other moments, statistical moments. So what it does is really what I told you a few minutes ago. So splitting, applying, and combining. So when I say, for example, group by sex, if it was only sex, for example, it will take the sex column and divide it where all the sex columns are the same. So in this case, it will take male or female. Then applying some function that is the mean, or in this case, it was extracting the survived column and then computing the mean, and then bringing it back together and showing me this final report on it. And yes, so this is a very common workflow. So grouping, and here I'm doing a mean. I could also do other things, for example, like filtering or joining, many other operations. There is an optional episode about this, Pandas number 2, where we go through many of these other methods, and I advise you to give a look at it, because it's a lot of things that you might be doing on a daily basis. But this for today is just a small introduction to how we work with tabular data. And I think I will stop here, and I will be available in the HackMD document to reply to your questions. We went through SciPy already, and I'm doing this because I think it's good for you to get some hands-on experience with this. So we have a couple of exercises. For example, this one can be very interesting to further extract information from this Titanic passenger list. So I advise you to do this in the time that we have left. And if you have any questions, please just ask, and we'll be very happy to help. And yes, I think it's interesting to actually try this in real life. So I guess we can stop now and give time for these exercises.